Broadly, I will say that what I do in this research group is about phase transitions and the disorderly systems. And particularly one of the things that I'm doing most at the moment is looking into how exactly water transforms into ice. It may seem like a silly thing or an easy thing for you to get, but it's actually not. And particularly how ice forms on top of something else, which is how it happens in nature. This is basically the focus of my research at the moment. At the moment, we have very little control about the formation of ice in biological matter. So what happens is that you do that, and then when you thaw the biological material up, you will sort of lose a substantial fraction of it. And so in very sort of looking at the molecular details of this process, which is what I do basically, it's really quite important to understand what's going on. And if you understand what's going on, then you can sort of engineer a novel cryoprotectants, so novel molecules that will help you having control of this formation of ice. So say that you are able to engineer a cryoprotectant that will allow you to save, I don't know, even 5 to 10% of the material that you actually store. Well, monetary speaking is a massive gain, right? Because you don't have to store that much. So the NHS is sort of constantly looking for ways in which you can improve the whole of the process. And then it's about sort of implementing these ideas as in theories in computer coding, which is a massive part of what we do. Running simulations, which is perhaps the bit that involves the longer time scale, because these simulations are complicated and long. It can sort of involve maybe months, this sort of stuff. And then you analyze them. So ice is obviously a material per se, but the formation of ice on something else really poses the question of which sort of materials can facilitate or inhibit the formation of ice. So in that context, this is one thing. But there are many other things that we do in this research group. Some of them are related to proper material science, so silicon carbide and this sort of material for automotive industries. And that is just a matter of choosing the application which is most relevant from the industries that we can sort of replicate and get microscopic insight into. Well, it's just the best place to be when you are a computational person, really. So all that we do is conditional to the availability of these computational resources, which we call HPC, high performance computing facilities. And Warwick just does a lot of them. We just have a phenomenal amount of resources in-house, and also the possibility to apply for computer time as well. So we have basically 3 tiers of computational power in the UK, Tier 3 and 2 and 1. In Warwick we have Tier 3 in-house, Tier 2 as a regional facility, and we can also apply to Tier 1. So it's just really a very convenient place to be. We are just beginning, I think, to sort of developing a collaboration with the ICE sort of keen people in Warwick. So one example is Professor Matt Gibson, who has a joint appointment between chemistry and medical sciences. So with him, we're trying to sort of converging onto some subject that we think we can sort of bring forward in the next future.